Let's look at this optimization problem. A wall 8 feet high is 3 3/8 feet from a house. You want to find the shortest ladder that will reach from the ground to the house when leaning over the wall. So the first thing you do is you always draw a picture. The picture is this. You have a house, then you have a wall 8 feet high that's 3 3/8 feet away from it, and you want to put a ladder, leaning the ladder over the wall to the house, and we want to find what the shortest possible ladder is. So our objective function is L, and it makes sense here to use x as the variable. X is how far the ladder is away from the wall on the ground. Basically, make sure we want to basically pick an x so that L is the smallest. And if we use the Pythagorean theorem, it's not hard to see that this is x plus 3 3/8 squared plus a plus y squared, and then square root for the whole thing. Of course, we don't want two variables, so we want to write y in terms of x. And how do we do that? Well, if you look over here, you have two similar triangles. We can set up a proportion. X is to 8 as 3 3/8 is to y. That comes from the similar triangles. And so we can cross multiply to solve for y. Xy equals 8 times 3 3/8 is 27. And so y is 27 over x. And so we can write L of x as square root of x plus 27 over 8 squared plus 8 plus 27 over x squared. And also notice that the domain of this function is all positive numbers. You really can't have the ladder be 0 feet away from the wall, and it can't be negative feet away from the wall. So we can say that let's minimize this by first doing L prime. And when you do the square root, derivative is 1 over 2 root, whatever's inside the square root, times the derivative of what's inside the square root. So the first one is 2x plus 27 over 8 times the derivative of x plus 27 over 8, which is just 1, plus 2/8 plus 27 over x times the derivative of 8 plus 27 over x. Derivative of 8 is 0, derivative of 27 over x is minus 27 over x squared, because 27 over x is 27x to the minus 1. Now the fun part, we want to set L prime of x equal to 0, and when you do that, remember that you don't actually need the denominator anymore, because you just want the top to be equal to 0 when you set the derivative equal to 0. So you have 2x plus 27 over 8 plus 2/8 plus 27 over x minus 27 over x squared equals 0. First thing you can do is to kill off the 2's, and then you can multiply the fractions. You can multiply the two factors on the right out, and when you do that, you get x plus 27 over 8 plus, or rather, minus 27 times 8 over x squared plus, minus 27 times 27 over x cubed. That's 0. And we can go ahead and just clear out the denominators by multiplying everything by 8x cubed. So we have 8x to the 4th plus 27x cubed minus 27 times 8 times 8, x, just x, minus 27 times 27 times 8, that's equal to 0. Alright, so now you want to solve this fourth degree polynomial equation. There are, I mean, the most practical way at this point is to either graph this or use a computer to find all the real solutions. And the real solutions end up being x equals 6 and x equals negative 27 over 8. It is possible to do this manually by hand instead of using a computer or a graphing calculator. One way of doing that is to go back here and notice that if you kind of think of this thing over here on the left as a factor, x equals minus 27 over 8 would in fact, it would actually in fact make this 0. And x equals minus 27 over 8 would also make this 0. And then from there, you can take this and divide this polynomial by x plus 27 over 8 to get x equals 6. Another way that you may want to do it, something that you may remember from pre-calculus or algebra 2, is to use the rational root theorem, which says that all the potential rational roots are factors of this number divided by the factors of this number. 6 is one of them. There are a lot of them. So guessing and checking is going to take a while. Once you do get these two numbers, you can actually go and say, well, first of all, minus 27 over 8, that doesn't work. Can't have a negative number. It's not in the domain. Then the next thing to do is to remember that this is not a closed interval we're dealing with. So we can't use the closed interval method to find the absolute minimum. We can, however, draw a sign chart. Remember, the sign chart starts at 0 because there's nothing to the left of 0. Put down our critical point and figure out if L is increasing or decreasing before and after this critical point. You can say plug in 1. That's something very simple. And if you plug in 1, you'll notice that you have a negative number. It's easy to see here. 8 plus 27 minus all of this stuff. That's definitely very negative. And after 6, you can try putting in something like 7 and calculating. Or if you go back here, you could actually say, perhaps, put in x equals 27. So all of these fractions go away and it makes your life easier. You should get a positive number if you do that. And so that means that 6 is a relative minimum occurs at 6. That does it mean it's the absolute minimum? Well, if you look at the function, it starts somewhere above 6, it goes down to it starts somewhere above L of 6, goes down to L of 6, and then it leaves it by going up. So it's never going to get below L of 6. So we can actually say that this is an absolute minimum as well. And so the shortest ladder is when x is equal to 6. So it's placed 6 feet away from the wall. But the question is, what is L? You'll have to plug 6 back into the original function L to get that. And you should get 15 and 5/8 feet.